Hi, good afternoon, ladies and gentlemen. Thank you for tuning in to the 6th edition of MARVEX Power Talk, brought to you by MARVEX 2021. I am Joyce, and I'm your host for today's session. I know it's been an eventful week, and at this hour, I want to congratulate you for being here, and we believe that today's discussion on integrating inverters for better energy savings in Acmv system designs will benefit you into achieving energy efficiency and saving costs in power consumptions. Well, before we begin, can I know how many of you are still working from home? Type Y for yes and N for no at the comment section. All right. Good afternoon. I've seen quite a few of you. We have also a friend from Indonesia. Welcome. All right. Any of you, those who are working from home, do type Y for yes. And those who are back in the office, please type N for no. All right. I see a lot of Ys. Well, I guess most of us are actually still working from home, which is actually good. But I guess you guys are actually missing your colleagues right now. Well, same goes for me. All right, those who are back in the office, please remember to stay safe. All right, once again, it's great to have all of you here with us here today. MARVEX Power Talk is a series of on-point discussion where leaders and experts converse and deliberate about the opportunities and challenges faced by the ever-growing, reshaping, and uplifting of the air conditioning, mechanical ventilation, and refrigeration industry. This Power Talk is brought to you by MARVEX 2021, which is the inaugural Acmv and our business event for ASEAN scheduled to take place from 1st to 4th December at Kuala Lumpur Convention Centre. MARVEX is jointly organized by MACRA and CIS and is held concurrently at Engineer, where we strive towards becoming the premier event for the primary source of Acmv and our stakeholders, while providing a unique platform for the growth and development of the industry in this region. We have prepared a short video to show you how you can leverage on this dedicated business event for your business.
MARVEX will create a new milestone for MACA and the Acmv and our industry. We are working towards become the annual premium business and trade event. There will be an important date on the trade calendar for the industry within the ASEAN region.
MARVEX is a platform that is driven by the industry for the industry. We look forward for this platform that provides our stakeholders with business networking opportunities.
Besides the all-day exhibition, there will be an industry conference, forums, and many more exciting highlights at MARVEX.
Yes, we are as excited as you are with MARVEX 2021. Be sure to stay on until the end to know how you can be part of this excitement. All right, back to today's session. Ladies and gentlemen, when you stay to the end of this power talk, you will learn to understand the starting method to reduce inrush current during motor start and by using variable speed pump with inverter or high efficiency motor to reduce energy consumption. And also, the focus of system efficiency is not just in heavy equipment in production loop. The hydronic network plays a major role in delivering the right energy transfer and eliminating the waste of energy by the means of white water delta T in order for the production system to work efficiently. If you have any questions that you'd like to direct to our panelists, feel free to type in your questions in the comment section and we will answer them at the end of the session. Our topic for today's Power Talk is integrating inverters for better energy savings in Acmv system designs. And we are honored to have two special guests with us today as our panelists. We have Mr. C.T. Wong, General Manager cum Director of ITA Electric, Sdn Bhd, and Mr. Derek Fong, Head of Technology and Application, Asia Pacific and Australia, Danfoss Malaysia, Sdn Bhd. Today's session is moderated by Mr. Eddie De Silva, Technopreneur and Committee Member of MACRA. Let me share a quick background to introduce our moderator for today. Eddie joined the electronic and electrical field since late 80s, where he began his career in Shin Daito Engineering Sdn Bhd as a technician and worked his way up until 1998, where he was attached with Sigma Emco as a technical supervisor and left the company with the last position of Head of Technical Department for an MNC company, Gravelgraph, as the technical manager. During his tenure in Gravelgraph, he actively trained team members and agents in hardware and software applications, while also involved in the building of his own business. Eventually, he moved on to his own company from 2011 till late 2020. Eddie is also a certified professional trainer and member of Chartered Institute of Training Practice UK. He was also an active ice skater and represented Malaysia in 1998 at the St. Louis International Recreational Ice Skating Competition in USA. He won several medals and one gold medal for Malaysia in this international event and moved on to becoming a part-time coach where his skating team was certified by the Malaysian Book of Records as the first team to represent Malaysia in the international arena. He is currently active as MACRA committee member and has contributed to the CSR, Business Development, Media, and Marketing Solution of MACRA. He also holds a diploma in psychology, US, and currently contemplating to pursue his master's. Currently, he's looking for collaboration to produce his own training program based on his recent book on leadership and self-management. Well, without further ado, ladies and gentlemen, let's bring in Mr. Eddie on screen with me. Hi, Mr. Eddie.
Joyce.
Hi, how are
Hi,
you?
Joyce. Thank you. I'm fine. Thank you. Thank you for the introduction.
No problem.
So I would
Right,
like to
over to
wish. Thank you. Thank you. I would like to wish a very good afternoon to all. Welcome to all of you to MARVEX Power Talk series. And since Joyce have already introduced, I'm Eddie here, and I'm your moderator for today. Today's topic is integrating inverters for better energy savings in the Acmv system design. We will be discussing about the current changes of material cost increase, which impacts the overall industry, and how we should be safeguarding the interests of end users, as they often have huge interest in operating expenses of life cycle costs of the premiums. Well, in this session, the focus will be on discussing of pump performance towards energy efficiency and cost savings, so that developers will enjoy and end users can achieve better power consumption, maximum demand, and efficiency. Well, as mentioned by Joyce earlier, we have a panel of two speakers who are experts in the field to share and further discuss on this topic with us today. And they are Mr. Wong, General Manager of CAM Director of EITA Electrics. Mr. Derek Fong, Head of Technology and Application for Asia Pacific and Australia in Danfoss, Malaysia. Okay, Before I introduce further the first panelists, ladies and gentlemen, do feel free to drop your questions in the comment section, stating to whom the questions are for, and we will do our very best to answer them at the forum discussion later. Well, now let me introduce the first panelist. Well, Mr. Wong is the General Manager cum Director of EITA Electric. He graduated in 1989, majoring in Controls and Instrumentation of Polytechnic Engku Omar. He started his career with Lim Kim Hai Electric Sdn Bhd as a Fuji Electric Inverter Technical Assistant, where he was mainly involved in service and maintenance. And in 1992, he was appointed as Fuji Electric Inverter Sales Manager in HVAC market as LKH Advanced Systems Sdn Bhd. And in 1996, he joined EITA as the Senior Manager, responsible in promoting Fuji Electric Inverters and Instrumentation System for HVAC machine and also in the industrial application too. He has specialized in fields of inverter for the last 30 years. He led and participated over 200 big and small inverter projects. He is currently actively promoting energy saving by applying an inverter and energy management system to the industry. Without further ado, let me invite Mr. Wong to join me on screen at the moment. Thank you.
Thank you,
Hi,
Eddie.
Mr. Wong. Hi, Mr. Wong. Thank you. Thank you for. Okay, so I would like to actually just wonder whether you are ready to do your presentation at the moment.
Yeah, sure.
Okay, good.
Thanks,
So I'll
Eddie.
pass the floor to you now. Thank you. Thank you.
Yeah. Good afternoon, all the participants. Yeah, I think in the past, this type of event, usually we meet together in a hotel room and we have maybe a light buffet. But today, we can see that because of COVID-19, we have to accept the new norm of conducting such event in front of computers to meet everybody. Okay, not further, from here that I would like to introduce, okay, today's topics will be the pump control system. Okay, you can see that my sharing today on the pump control system, motor starting method and protections, fundamental of inverters, multi-pump system. Pump and pump controls are an important part of today's technology in the building and water industry. The task of the pump is to generate pressure and flow to transport liquid and also used for various kind of cooling system. Pump usually is driven by with a motor, electric motor at a constant speed. Okay, in here, I would like to just quick refresh type of pump that used in the building industry. You can see from the slide that I think commonly we use, I believe everybody, if they say you're in the Acmv industry or HVAC industry, you're familiar with the centrifugal pump, chill water pump, sump pumps, booster, and also that fountain, maybe followed by fire pump that in the building industry. And also that you can see in the water industry, they also include those like screw pumps, circulation, transfer pumps, and also sewage pump that you can see that. Okay. What is the pump control system? Pump control system or pump controller provide a full range of function for a single and multi-pump system. The function basically that include the components of pump controllers, timers, a start-stop by motor starters, protection device, and also that the measuring instruments such as flow meters or maybe that a pressure switch or pressure transmitter. So all this is basically that is the component we use in the pump control system. Let us quickly go through the motor starting method that commonly used in Malaysia market. You can see here, start from the direct online, star delta, auto transformers, soft starters, inverters, or the other terms that we call variable speed drive. Okay, so let's see the slide that on the direct online starters. It's simple. For direct online, you need the component is MCCB. Basically, that is to protect the short circuit or overcurrent protections. Then followed by contactors, and also the thermal overload is to protect your motor from overcurrent. So all these devices basically that easily you can connect them up to become a direct online starters. Let's look at what is the advantage on the direct online, especially on the three-phase induction motor. Basically simple and low cost. And also that you not require a big space for this direct online circuit. And also that the advantage is provide 100% torque or more at the starting time. Okay. The disadvantage of direct online, as I say, the inrush is high. It's around 6 to 7 times of the rated current. And also that the inrush, because of inrush, sometimes there will be excessive voltage drop in your power line. Okay. Then, and also that it will be mechanically harsh to the motor because that it will be energized full voltage to the motor. Okay, you can see that this is the actual pictures in the panels with the direct online. You have many circuit over there. You see the actual pictures inside the panels. Okay, so the star delta, basically that compared with direct online, there it will be the extra component, 2 more contactor on that, main contactors, delta, star, and plus the thermal overload. Okay, and the connection will be 6 wires compared with direct online, only 3 wires to the motor. Okay, the circuit will be start with main and star point. After some time that you need to cut in the delta point. Okay, so when you cut in the star point, it will be basically that cut in 50% of the voltage. Okay, that's to help to lower down the inrush. The advantage on that, basically that still additional 2 contactors, simple and relatively cheap compared with the others reduced voltage starting method. And also that this will be draw 4.5 times and above. Okay, on the full load currents motors. The disadvantage of this star delta, basically the starting torque is low when you accelerate it up. Okay, then when large surge current due to when you open circuit on the star and cut in the delta contactors. That is the disadvantage of this star delta. Okay, this will be the actual pictures. You can see that 3 contactors on your right hand side, followed by our timers. Let us go through the third method on the motor starting methods, the auto transformers. Okay, the difference compared with the star delta is only additional on the auto trans. Okay, so you still need the 3 main contactor over there. Basically the main contactor, and followed by the star and the also that different tapping on the transformer. Usually there is the 3 tapping for the auto tran. You can tap 50, 65, or 80%. You see, to start the motor based on the characteristic. You see, so this is the important tapping. Basically, that different type of tapping will generate different type of inrush current. Okay, when the motor reach 80%, basically the star contactor will release, followed by the transformer contactors. So only left the main contactors energized to provide full voltage to the motor. From here, you can see that there's only 3 wire connection after the delta's contactor cut in. Very close to the star delta, the advantages, basically that simple, but we can deliver high torque. Inrush current, it can be lower compared with star delta. And also disadvantage is basically more expensive compared with direct online and star delta. A bit bulky compared in size. So these are the basically disadvantages on the Autotrans. Let us move to the picture. On the bottom part, you can see that orange color basically is the Autotrans. Okay, so this will be actual pictures on Autotrans. Soft starters, I can see that this is the latest technology. It's an electronic starters combined with thyristor technologies. The advantage of soft starters basically that no moving part compared with like conventional star delta. You need a contactor that is a moving parts, and also that much more smoother because that the acceleration vary according to the voltage and time. It's not like others basically cut in 50% or 75%. Of course, when you basically smooth, then the basically reduction of shock on the mechanical side. The disadvantage on this basically that high cost compared with conventional starters. And reliability, I can say that because electronic device, sometimes that you might be sensitive to the heat and also that the environment. The latest, I can see that inverter, okay, still connection is like a direct online. You need MCCB, contactors, inverters followed by motor. This will be the best at this moment. The technology in town can help you lower down the inrush current. The best, as I say that later, I will have a comparison on the tables. Less mechanical stress, high starting torque, able to have energy saving, better in protections, but of course, cost is the most expensive compared with other starting methods. Anyway, still an electronic device, still sensitive to the heat, humidity. Another thing is basically that drive or inverters will generate harmonic noise to your power line. Okay, you can see the comparison table over here. That is the direct online, star delta, and Autotran, soft starters, and inverters. We just see that there is the starting current. There is a difference between all the different motor starting methods. Power factors, also that inverter will get you the highest power factors. Start stop, as I say that the most smoothen and also that basically less mechanical stress to your line, motor, or either production line. Because of the VVVF technology, variable voltage and variable the frequency, easy to control the speed compared with conventional way. There's no way for you to control speed. You need a gearbox for that to reduce that. High speed operation. For inverter, actually, you can be double up the speed if you say you really want. You can run at maybe 80 or 100 hertz. That is basically that able to see the fault message. Later, I may go through the protection. Remote control. As I say that conventional is only you can be start stop. You cannot get any data on the basically trip status, what is the overcurrent level. But with inverters can show you what is the trip message. You can do that by using the RS-Wi-Fi and also the display. Energy saving, later I will touch on that. A type of protection, you can see over here that direct online or Autotran star delta, same. Basically that they're talking about overcurrent or phase loss. Soft starters, slightly more. Inverter, at this moment, the protection is still the best beside overcurrent, over voltage, overheating, and also the short circuit on the inverter output, ground fault on the inverter output, you see, and also that you can connect the PTC to the inverters. Let's quickly explain a little bit on the basic of inverters. Inverter technology, as I say that, is three-phase coming in with diode, rectifiers, and also that smoothened by capacitor and switching it back to the IGBT, okay, by IGBT to the motor. So this IGBT will switching back a sine wave, okay, to the motor in order to get the AC motor running in the VVVF format. Okay, so this is the basic of inverter, and also this inverter name is come from here. They will be invert from AC to DC and DC to AC back. Why inverters? Okay, I think everybody that maybe that interested on this is very important. When, if example, you have a pumps, should I put inverters or not? Are you consider that? So what is the criteria we need to consider? First, this pump need to control the speed or not, or able to vary the speed or not. Are you looking into low starting current? Okay, and also energy saving. That is the important criteria. So please remember that. A booster pump, maybe you can see that those days is controlled by a on-off pressure switch, or with a little bit more advanced is controlled by the control valve. But today you can see that you can remove a control valve and control by the inverters. You see. Okay, you can see that all this control, just now you need a pump controller to do that. But today, the inverter is getting much more smarter. You see, you can basically skip the pump controllers. As I say that, inverter able to run independently to control the motor speed and to fulfill the pressure demand. Let us go through that cascade control that already built in the inverters. Like example, you have basically that M0 pumps to M4 pumps. So the pressure will be have a pressure sensor to measure and feedback it to the inverter PID. Okay, so assume that one pump is 1 bar. So you have basically that 5 pumps over here. So we can deliver 5 bar to the main maybe water line. So from here, that like example, I start the first pump. So the pump is vary. Okay, if the inverter run to maximum, still cannot fulfill the demand, the inverter automatically will call M1 to coming in. Okay, and if they say that still not enough, like example, the demand is talking about 4.5 bar, then maybe that you have to run all the 5 pumps and vary the M0 pump to be half in order to get 4.5 bar. So this is the we call fixed type. Okay. Another method is with a floating type. You can see that you can variable the M1. Okay. So first the M1 will variable to maximum speed. If the demand is more than that, then you need to call for M2 to start, right? From here, you can see that inverter will release the M1 and cut in direct online, and followed by M2, soft up the M2 by inverters and vary the M2. Similarly, if you say that the demand still cannot fulfill, you can go for M3. Similar that M2 will release direct online, then followed by M3. So this is the, as I say, the floating method on the cascade. You can see that today inverters is getting smarter on this. And also that we have a mutual control. The difference is just now all you need to go for hard wiring. But today that you can be interface each others, communicate each others with the inverter, master, slave. So basically that similar master will run. If you say the master that feel, oh, maximum, I still cannot fulfill the demand, I will call for the second pump to come in. What about the master fail? As I say that slave will be take over as a master. So you can see that with this technology, the energy savings will coming in. Let's see. Well, let us look into the energy saving on the affinity law. Okay, we just concentrate maybe on the motor output is proportional to the cube of flow. Okay, so that is the affinity law for the centrifugal load. So please remember that on this formula. And over here, I do a quick summary. You can see that just now, as I say, if the inverters or your pumps, you cannot vary the speed, it's no point for you to consider inverters, because that inverter efficiency probably maybe that I put it 97%, or maybe the best you can go is 98. You still need to consume more energy because of the inverter efficiency. But when you can able to reduce the speed like 10%, or maybe you can see the highlight over here on the green colors, from the 80%, basically that the speed, the energy consumption probably maybe only need 54% of energy. So this is a beauty of inverters, that it can help you to save energy. Let us look into the quick calculation on the basically on the pump side. You can see the example that the 30 kilowatt pump or AHU that you can run on the 80% basically flow rate. From here that you can see the without inverter, maybe 1 year you consume 15,100, even though I put a very low electricity rate. And also that with inverters, you can see just now, the consumption only 54%. Okay, I put it higher, you need consume 60%. So from there, the ROI only need 1.6 years. Okay, so bear in mind that with the latest technology, we can help you to save more on the energy. Okay, thank you. I will hand it back to Eddie. So if you say you have any question, please feel free to put in the chat group or comment in the chat group. Thank you. Eddie, you are mute.
Okay, sorry. Thank you, Mr. Wong, for sharing autos and also controls on high efficiency of using the motor. Your sharing was indeed insightful. I shall save the questions to the forum discussion later, right?
Yeah, sure.
So, okay. Ladies and gentlemen, let's move on to our second panelist, Mr. Derek Fong, the Head of Technology and Application in Danfoss, Malaysia. Well, Derek, let me introduce Derek. Derek has been an active practitioner and trainer in the control systems engineering in Acmv and HVAC system ever since year 2003. In more than 17 years, he has conducted a large range of proven systems, case that's analysis, and also he is now heading the core engineering and application team. He and his team has been using simulation software to help clients to achieve high performance results. He attended more than 1,000 thermal control systems globally with hydronic installation and conducted 40 to 50 training sessions and also seminars yearly in Asia Pacific, Australia, and Europe. He has been performing analysis, commissioning, and also applying proven effective solutions to his client. He has helped end users to achieve up to 60% of the energy saving and improving accuracy by reducing 70% of maximum deviation. Well, with that said, let's invite Mr. Derek to join us on screen. Hi, Mr. Derek. How are you?
All of you. Thank you, Mr. Eddie, for the kind introduction. Hello.
Yeah,
Yep.
hi. How are
good.
you?
I'm excited to be here, and I'm glad for the participation.
Okay,
So,
that's good.
Can everyone
I think
hear
your
me?
camera is a bit vague. Could you please focus more? I think okay. That's nice. Okay, that's good. All right, I'll pass the floor to you. No, I would like. I
Yes.
would like not to. I would not like to delay you
Okay.
further. Right. Take care. Okay. Bye.
All right. All right. No problem. Thanks a lot. Goodbye. See you again. So, all right, and let's begin. Right. So now, in this topic, we'll delve a bit deeper on the system dynamics. And like Mr. Ellis said, for the past 70 efficiencies for end users, especially, and also I've been working globally with some designers also to increase the system performance. So it's not just saving energy. So what is not really very commonly associated with energy saving is also save energy without running under capacity. So not to compromise the comfort, because that's still number one goal for HVAC. Skip that myself for the past years. So now a little bit in the beginning right here, when we talk about efficient technologies, and are the key technologies that we regard as the key components. That if you look at the left-hand side here, where we call magnetic levitation compressors, in fact, it is actually a centrifugal compressor, which is oil-free, and it is powered up by a small voltage to actually lift up the compressor and rotates without friction. So it's a fully vacuum, and actually it can rotate up to thousands of inverter, and this has been this decade has been one of the most demanded component or is, and we have been having more than 80% market share for this. So also the trend is also working on this way. And in the middle, we also know that inverters are integrated to pumps and fans, and also electric, also permanent magnet fans are also coming into the market. So Singapore is also, and Europe is also adopting these new technologies in inverters in the fan. So on the right hand side, what is also we call pressure independent balancing and control valves. And this is in short, of course, we call it PIBCVs. In air handling units or in fan coils. And then if you're dealing with district cooling, we even have sizes. This is actually available for energy transfer stations, where if you go to Putrajaya or the topics that we are going to touch today. The first one will be a basic control into the dynamics of affinity law. So we are going to compare a fixed speed and variable speed dynamics. So pair. So what happens to the curves in the pump that has no control? And with constant pressure control, then the third one will be. And after all this, that we'll actually analyze one of the case studies together, what we actually would consider a very efficient system. And what is this actual system that we have really improved? We have done this worldwide on hundreds of case studies, and I'm picking one of these in Malaysia to actually present in this seminar right here. So now let's go to the basic control loop. And this is one of the topic that, of course, when we see in universities, it's just a few block diagrams. But if we look at always acting as an independent controller as well, so you and link it to the inverter, then to also monitor the pump there. Okay, if we look at the inverters, is that it consists of the controller, and this is the highlighted area is where you can actually adjust your set point, and it gives the 0 to 10 volts signal. Then the variable speed drive will actually modulate the power output to the pump motors, right, which is this part, and the motor will drive the pump impeller, the speed. So after that, so the pump will primarily actually give the output of pressure or differential pressure in this case, and the flow at the same time to the system load. So, all right, so the process goes back, X is the pressure point in the system, then this is where it takes the feedback as an analog input to the summing junction, all right? So summing junction is where the set point and the feedback is always compact, and it sends the error to the controller so that it can process the differences and decide what is the signal that is supposed to be given to the drive to modulate the model. All right, so now let's look at a bit of the control behavior. And when you look at the control behavior, let's say, for instance, if you have the set point, and if you start up a pump, and this is normally what we see, if we start up the pump, and the pump will start to ram up and build the pressure up in the system. And then you would have a little bit of overshoot here when we look at the anatomy of this behavior. So we always call this either load starting or load disturbance. Then when it comes up here, we call it overshoot. Right, so now we always want to get close to the set point, and also by judging how fast is also very important. And the third point here, we always call it the settling time. So we always want to reach a steady state. So we always remember before reaching steady state, the dynamics we will have dynamics from point 1, load disturbance, overshoot, point 2, and point 3 will be the settling time. So these are the four of the most important criteria. And then this is not what we always see in the system. And this is often what we see is a very theoretical point in universities. And if you go to sites, you might see larger overshoot and also oscillation without settling time at all. And that calls for a lot of expertise in the field, from the field to actually tune the PID, that is actually PID, a proportional band, integral time, and derivative time in the controller. And of course, this is usually it's a try and error tuning. If not, we could employ Ziegler-Nichols or Thiers-Lieben tuning techniques. But of course, bear in mind that if we tune PIDs, it's like putting 3 bowling balls vertically together. So imagine these are bowling balls. PID is like balancing them vertically. So if we are not tuning it well, it could fall off of balance. All right, so now let's move to the next topic. And of course, this is one of the number 1 reasons that we know that inverters, if you couple with pumps or fans, especially centrifugal pumps or fans, they respect affinity law. And this is actually to simulate here, the intention of this slide is to simulate the energy savings in the curve. So we all know that the flow rate, if we get to actually tune the inverter flow, we reduce the dial down the flow rate to 10%, and we get to the end result is that we get to save about 27% of the energy. All right, and at the same time, if we actually reduce the flow rate down to 80%, we get to save the power by around 49%. So this is actually a very quick reference that you can see in the affinity law without factoring all the rest of the inefficiencies. But of course, if we want to be meticulous, then we would actually factor in all the mechanical inefficiencies in this equation. But we are looking at the surface right now where it could give you a very quick estimation by reducing how much flow rate and what other savings do you get. Of course, there are 2 curves right here. And what I was actually mentioning is a result. And in between, you have differential pressure savings. So like I said, again, I would just like to pinpoint, if we save 10% flow rate, and this is actually proportional to flow square, then we'll be saving about 19% differential pressure. All right, and of course, again, 20% flow rate would save about 36% differential pressure. So of course, unlike power will be even more. All right, it's in power is proportional to flow Q. So this is a simplified equation right here, right? Not to go too deep. All right, so I've marked down some of the charts. Let's say if you save 70%, 30% of the flow rate, then this is the equation that is deriving these savings. All right, if it is power, flow rate is dotted here. If it is power, then it's 3 in cube. So this is where you get these savings. All right, so another way to look at it is that if we look at systems that have pump running, a single loop, and if you have a fixed speed without inverters, a pump that is fixed speed, and what happens if you actually close the control valve and regulate the control valve to about 50% of the flow rate? And this is a very simple comparison, and most of the end users, they want to have a simulation to look at this. So when, of course, control valve closes, pressure builds up. And this is the flow meter. So we see like 50% of the flow rate. So let's do a quick charting. So 50% of the flow rate would attribute to still 90 kilowatt, which is 90% of the energy consumption. So even if we don't have inverters, by reducing 50% of the flow conventionally with a control valve in a single loop, then it will only reduce about 10% of the energy. But if we actually if we actually have a drive integrated to the pump, then of course, if we reduce the flow rate while keeping the control valve fully open, all right, or we don't even need a control valve in this case to regulate the flow, regulating to about 50% with the with a cube logarithmic savings, then it will be at this point. So this is about saving about 85% of the energy while reducing about 50% flow. So this is just a very quick comparison in just a single chart. All right. So now you have an idea of the affinity law, how it works, and some of the pump control dynamics. But how about if we look at it in a way that we put it in a system, and let's say this is the hydronic systems where we have a variable primary systems. We'll go a little bit deeper onto that later. And in variable flow systems, and if we do not have a variable speed drive, all right. So what will happen? Now this is full load, and we call this the hydronic ladder. You can see that this ladder is like horizontal, right? And you have fan coils and air handlers along the line in parallel. And then you have like two-way control valves and manual balancing valves. So now, in full load, not much pressure is built up. So let's say all the control valves are open like 100%. All right, and the bypass, let's say, is fully closed right now. Now, what happens during part load if there's no pump control? It's running on full speed, like what we saw just now. If it is running on full speed, the red color area is where the pressure builds up. Whenever the control system, whenever the system runs on partial load. So that means some of the control valves are closed. The pressure will start to build up because of hydraulic interactivity. All right, so now you get the picture, no pump control, and all these red lines becomes like wastage, more pressure than required. All right, so and you can see because of frictional losses, this ladder becomes a lot smaller, right? So, but when it closes, the pressure at the furthest point will become also as great as the pressure nearer to the pumping source in this case. All right, so let's move on a bit, and I'll actually expand that a little bit. That means if we actually close the control valve, all right, let's say the control valve you have about 100 kPa, and you also have 100 kPa across the strainer and the coil. So once this control valve closes a little bit, let's say closing about half of the flow rate, then you have pressure transferring to the control valve because that's the smallest orifice now, for instance. All right, and the pump pressure head will be actually also transferred to the control valve right here. So what you can see right here is that it's not something that's linear, and it's exponential increase of the pressure from all fittings or even the coil has been transferred to the control valve. And this is a dynamic we have to remember. And if we look at, and if we plot it into the pump character, the curve, and before we even plot the pump character, and if as we are designing the system, we would actually put all these mechanical components together, and with the design flow rate, we will be able to stack up the system curve. And the final system curve, let's say the yellow color part, we always say, okay, that's the pipe and fittings. Then you have coils, or we call it heat exchanger, a design flow, which is each one has its own pressure drop. And finally, when you put all this together, you have the system curve. And this is where you select your pump, right? So, and this is when you select the pump with all the pressures gathered together. And of course, this is where you get the impellers to be compared, whichever will give you the right capacity and also the right operation point. Or you call it the best efficiency point in this abbreviation here, BOP or BEP. So now with the pump curve and system curve defined, so, and then this is based on full load, all right? So what happens if the control valve closes, right? Like we see during part load. And what we know is that this red color is the control valve, and the pressure would actually be transferred to the control valve. You can see that the red color area, before that the pressure drop was less, and the new pressure drop is actually bigger, right? So you can see that what is left to the equipments right here, two of the rest of the equipments, the pipe fittings and the heat exchangers, are actually a lot lesser exponentially. And exponentially, the pressure, which was actually around something like this before, was at this area. All right, so now of course there's some formula to back this up, but of course here on the surface part, we want to keep it as a simple illustration. All right, so of course pressure builds up when control valve closes. All right, and then we'll have a lot of hydraulic interactivity in the system. So one valve closes influences the rest of the valves' performance in the system. All right, so now, okay, this one I won't elaborate more because this is what we have covered just now. No control. Okay, sorry, no control. That means pressure would build up. Okay, so now let's simulate another point. So what we saw just now was something quite, I would say 50% of the sites, they still have fixed speed pumps. And sometimes even if they install variable speed drives, and when we go to the site and when we actually look at the system, it's running maybe about 45% hertz, because no one really knows what is the differential pressure set point for the pumps at that point. So it's a lot about trial and error. When we ask the end users, how do they operate, then we'll just put the fixed speed a bit lower and then we'll just fix it there. So they try not to go into very complicated system. But there are some sites also, you can see a certain percentage. You can see that the differential pressure sensor is across the main header right here. So differential pressure sensor consists of a high side. These are the tubings where you take feedback. Tubings on the low side and the high side. So it takes pressure sensing point from these two, and then it actually sends the signal back to the inverters, because inverters can act as controllers. And then it tells, whenever the control valve closes in the system, if pressure builds up, or before it builds up, then it tells the pump to reduce the speed. Now, so what is the system dynamic like, you may ask? And so of course, full load, doesn't matter where you mount the sensor, it's always the same. You have frictional losses when water molecule travels around the system. So now, what happens if some of the units closes and just a few is left open, right? So pressure do build up when you still have sensors across the header. And yes, you may save energy, because if you compare this against no control, it is this part of the area of the pressure that we get to reduce. All right, so this is the other part of the pressure that we get to reduce. So you still get more pressure than required in some areas or most areas in the system during part load. Right, it's not the most optimum, but at least we get to save energy. And how energy is saved is, if we look at because this is what we call constant pressure control. And when it's mounted across the header, that means that this 300 kPa would be actually the set point. So if it's above 300 kPa, it will reduce the speed. If it's below 300 kPa, the variable speed drive would actually increase the speed. So it is a proportional control right here. And of course, whenever we can see that this shaded area is where the area that is potential energy saved. So that means if the flow rate is reduced down to 50%, then the area of energy saving is right here. All right. So you can see this is around 30% of the energy saved without accounting for a lot of efficiencies at the moment, right? So this is like taking at the slightly at the surface area at the moment. So, okay. So now what happens if, like, let's say some control valve closes, right? So sorry, yeah, some control valve closes, then the control valve pressure doesn't actually go up to this area. So there will be a new pump curve also when you have constant pressure control. Instead of operating this much, then the pump curve will become smaller together with the system curve. It moves. All right. So now, of course, that is also what we conclude on the pump's constant pressure control dynamics. And let's move to one of the most, where we encourage most end users or designers to actually use is what we call proportional pressure control. And how do we achieve proportional pressure control? And this is one of the most efficient method while keeping the right capacity at the system. And most of the time, and this critical unit is very important, and most of the time it's not necessary the furthest. All right, so I repeat it again, it's not necessary the furthest. The critical unit is the highest pressure drop unit in the system. All right, bear in mind. So now, so what is important right here is that the sensor is actually placed, differential pressure sensor is actually placed across the critical unit. And right here, what we can see is it's linked back all the way to the pumps. And of course, whenever the system is running on partial load, and what happens to the system dynamic? So when it runs on partial load, then the pressure won't actually build up in some areas. All right, so this will help you to, whenever you keep the pressure constant across the critical unit, then the rest of the units which require lesser pressure will have more than enough differential pressure in the system. All right. So again, I repeat that again. If we keep the pressure constant across the critical unit, the rest of the units in the system actually they achieve more pressure than required, even during partial load. All right. But of course, the biggest challenge will always be how to locate this critical unit, right? So we won't go too deep into that now. And okay, so now another question is that what are the best combinations when you want to achieve the best pumping efficiency? Of course, we will need and these valves are considered conventional control valves plus manual balancing valve are considered outdated, and Malaysia is actually taking the lead in Southeast Asia. We can see most of the designs now don't call for this kind of components. They actually integrate pressure independent technology, and I'm very happy to see that. And it has been like over the past decade, the whole adoption of this technology has become more or less matured. 80 to 90% of the tenders actually are open. And in the early days, I would say if we compare some commercial versus technical side on this part, a lot of people ask why this is like twice or 3 times higher than conventional control valve. But still today, they are using this new technology. It's it's very encouraging that more people are putting focus into efficiency, precise flow balancing and control. So, well, this is exactly what I've mentioned about proportional pressure control. And it allows you to have a lower minimum set point, minimum pumping set point here, which is like say 100 kPa, which is placed at the critical unit. And whenever the flow reduces, the pump will be able to reduce the pressure at the same time. So hence this blue color shaded area is the energy saving part. So for instance, if we have 50% of the flow rate, then the pump curve would be even smaller. So the potential energy saving area is at this area. All right. So of course, in reality, most of the time, this curve is actually not a straight line. In fact, this is where I'm very optimistic by implementing a lot of this solution right here, is that the curve is actually more logarithmic and it saves more energy than the theory. All right. So now we have been talking a lot about simulations right here. And of course, I'm very happy to share to you we have been given opportunity to actually work on real case studies to improve systems. And we are very proud of it to say that, this is where we find the significance in the system. And like I want to say again that we regard these are the three efficient technology that most end users would look into. And of course, given today that most end users are very energy conscious, and it puts a great pressure on top of our shoulders as engineers, and we need to help them to achieve the baselines, right? So now, and as a norm, most of the investors or end users, where they would put the most money. Of course, when we talk about the most money is where they put in the heavy equipments, right? So which is always concentrated in the plant. All right, and this is a system where we have this kind of technologies in the existing plant. But the thing is that the most underestimated part is always the hydronic control and balancing. And most people think that valves do not play a major role because they are thought as peanuts in the system because they are a lot smaller than heavy equipment, right? But allow me to tell you this, that this is not as expected as a peanut that doesn't deliver significant performance. So if we talk about variable speed chillers, now we are moving to chillers, from pumps to chillers. Conventional chillers, the typical curve in single centrifugal stage chillers, how they perform is that in full load, they are more efficient, right? But in part load, they are less efficient. Now, for this instance, is that at full load, let's say the set point is about 6 Celsius, 614. Nowadays, engineers, they like to have higher delta T, right? So everyone is stretching to about 8 delta. Unlike the past decade, we always see around 5 delta or 6 design. So I'm very glad to see this. And this is where I would say if the system is operating on part load, that means this is going to consume, okay, this is about 0.5 kilowatt per ton, right? So, and this is going to consume about 0.65 kilowatt per ton at 50% load, for instance. And now we see a surge of 30% higher energy consumption at 50% load. So this is one of the typical curve, but many manufacturers you might have different curve. But what we know is that essentially right here, systems doesn't always run on full load all the time. When system runs on part load 90% of the time. So now, which means it brings us a question: what is the best fitted variable speed compressor system? And the load is always varying, right? So to fit the load, the demand to the supply, and right here we also need to regulate the compressor speed in the chillers. So variable speed chillers come into the picture for the last decade, and it has been like this 7 years is becoming increasingly popular. And these chillers, they have sweet spots, meaning that if it operates between a certain load range, then it will be operating at a certain efficiency. So of course, if you want to fully occupy most of the capacity, yes, let's say 20% load and 80% load, it will be most of the time below 0.5 kilowatt per ton. But of course, it depends on what is the temperature set point and how the condenser is sized. Now, we always remember that the lower the load, the more efficient it is. For example, if it's 50% load, then this can be around 0.4 kilowatt per ton, compared to this was around 0.65. So the differences are huge in this. It's almost about between 60 and 70% difference in the energy consumption during part load. So, all right. So now let's delve a little bit deeper into the application on the overall. So this is how we see the typical variable primary flow application. And that and this is actually representing a few hundred coils. It's not just 4 coils. I could not fit 300 coils in the system. And this is the system where we get to replace inferior valves. And once we replace the inferior valves in the system, and also what is important right here is also the bypass is important. And most of the time you can see there's a butterfly valve here, and to compound the problems, they put an on-off butterfly valve, which is very heartbreaking at those times. And of course, this also can be changed to pressure-independent technology. It's also very important at this part. And sorry, I will roll back a little bit before we come to the analytics. Now, when we look at systems, we very often look at the kilowatt per ton, and in a very crucial energy. The first look on the surface, whether you know whether this system is sick or not, or is consuming more energy than required, is that we look at the supply temperature and the return temperature. If the design is about 8 Celsius and its differences, delta T is about 8, and the actual delta running, design is 8, actual delta is about 3 or 4, then we know there's a opportunity for optimization, right? Because whenever we have low delta, definitely there'll be problems in the system. Definitely there'll be inefficiency in the system, whether the coil is clean or not, whether it's over pumping, whether it's balancing is out. So that comes to the analytics. So right here, when we dive deep into the analytics, the very first thing we look at, we take the data of a 1-month data across the main header, and this is what we see. We overlap for 24 hours and for a month. And what we see was, we know that whenever we pick up this data, we saw a delta of about 3.2 Celsius, which is way below 8 delta. It's about 40% right now. So there's a huge gap there. And once we replace hundreds of valves in this system, and we get to stretch it, so it's about 99% close to the design delta. Of course, when we stretch delta, then when we get very precise flow, then this is a very good opportunity to actually reduce the pump speed, right? And this is where we actually connect the pumps to the critical unit, where we have a hydronic calculations team to back up with a software to calculate and locate this critical unit. So we get to save 60% of the flow. Now, what is more important is that not just the savings right here, very importantly is that if you look at the temperature's behavior, this is actually oscillating and it's overlapping one another, right? This data. This is a lot of oscillations in the system when a low return temperature is sent back to the chillers at times. And this is also considering the bypass is not stable. So unstable supply and return temperature reduces the lifespan of the chillers. So overall, we are talking about the OPEX, the life cycle of the system, not just energy right here. And we managed to reduce about 70% of the maximum deviation. And this is the baseline, or I would say one of the key behaviors that we look at the system. So of course, return temperature can have slightly bigger maximum deviations, but of course, compared to these ones, it's a lot smaller. Right, so less surging, because when chillers, they receive low return temperatures, you start to see chillers making noise, right? So especially centrifugal chillers, single stage. So now, what is the main result of the entire system impact? So we do not just see numbers that on the kilowatt per ton, we get to reduce 26% on the overall, all the heavy equipments when are stacked together. But we look at the entire plant character, which this is the character where it's sum up of all heavy equipments here. So of course, the very first thing besides active energy saving, 26%, and this is where we see a maximum demand of 20%, which is reduced. So there's a lot of money there. And what is more important in this characteristic, that the chiller plant character is also very stable during part load. Let me ask engineers who actually deal with chilled water systems. How many times you go to the site when it's during low load, and how much are the problems that actually popping out whenever it's nighttime or low load? I mean, you always get called to the site to attend problems, and you get BMS guys, you get chiller guys, and it seems that during part load, the most unstable time, and that's where the most problem occur. And this is why you see that the curve before, these red colored dots are before retrofitting the system. And you can see there's a wide maximum deviation right here. And we, even by less than 30% load, we were relatively stable at this. And you can see that the lower the load, the more savings we get, the more efficient the system for magnetic levitation compressors. All right, so when you have VSD in the compressors of the chillers, then it operates better during part load. All right, so what happens to the end? So what will end users do when they see this? They will do their best to do the enveloping of the buildings. So they'll start to limit the air leakages, they'll clean the coils to make sure that the load becomes even lower. All right, so to maximize the benefits. But of course, jointly as a team in Danfoss, we don't only manufacture and supply products through our partners, we do help our, the stakeholders to achieve the maximum benefits. So this is, as an engineer, that's our responsibility. And before that, we also, looking at the longer term right here is that if you look at energy savings, and this is where we go deeper and a broader, in a longer horizon also as well. So we usually take the benchmark of 3 months energy efficiency by, this is actually telling us that it's about 0.85 kilowatt per ton. So the blue color part is about, it's actually reference ton per hour versus kilowatt per hour per month. So this is cumulative result. We got to boil it down to one ratio, right? So now right after the retrofit, of course, we get to save about 26%, like you saw just now in the first slide, the slide previously. And then, of course, it takes some time for us to fine tune it. And we'll reach a point where the efficiency is already maximized. We have maximized the efficiency. And for over many months right here is stagnated at 0.55 kilowatt per ton overall. All right, and we save on top about 9% for the end users. And this is where we disengage from project. So this is a services combined with product. So it's not like sell and forget, right? So this is very important. Help your stakeholders to optimize the system. Right, so now, big question. Yep, we got to improve the system. And what is the investment return rate? Or you might call it ROI in some cases, right? So these end users, they have spent about 380,000 euros, which is 1.8, times 5, 2 million ringgit. It's achieved less than 24 months, right here. And every month of ROI is calculated. And this is the case in Malaysia. We have been using euros because it's internationally presented on this case. Right, so, all right, so this is one of the almost the last part coming that we encourage engineers to look into one of these. When we talk about inverters, there's harmonics. I wouldn't cover that in this topic because it's a very huge topic and this is very electrical related. And we have a software we call MCT31. So we also talk about THVD, Total Harmonic Voltage Distortion, and TDD. And of course, this is actually, we are talking about the compliance of IEE 519-2014. So we have a partner, NYKK, who are considered the experts and the very forefront of actually supporting inverter services. So this is actually one of the part that you can refer to them. All right, so now I hope you enjoyed this session, and please, formulate your questions. Let us know what are your thoughts. So thank you for your time. I would pass the session back to Mr. Eddie. Thanks a lot. Thank you.
Okay, thank you, Mr. Derek. Hello. Thank you, Mr. Derek.
Hello. Thank you, Mr. Eddie. Hello. It was quite a fun right there. Great.
Yeah, thank you for sharing your valuable experience with us and your most insightful tips.
Pleasure.
Okay, well, to our friends in the audience, feel free to ask any question at the comment section and remember to mention who the question is for. Now, we have heard from both parties. We shall move on to the discussion forum and tackle some questions from the audience. Let me invite Mr. Wong to rejoin us on the screen.
Hi, Eddie. Yeah, I'm back.
Hi, Mr. Wong. Welcome back.
Hello, Mr. Wong. Welcome back, Mr. Wong.
Hi, Derek. Hi.
Okay, let's begin the forum. All right, ladies and gentlemen, key components manufacturers must have engineers who have construct system simulations to strengthen the value of proposition, which must be clear from the beginning, and it is also imperative to look into reliable products, quality, and also lifespan of the materials used to ensure that the end user's interests are protected from the early stage. Okay, before we end this session, can we have our panelists give us the number of key takeaways for our audience in line with today's topic? Let's start with Mr. Wong first, okay?
Hi. Okay, the important part for the engineers or basically that the user over here, try to basically that make use of the latest technology. As I said, that like in my slide, I presented it talking about the VSD. So the three criteria that important to apply that when you consider the VSD or inverters. First is we are talking about the whether you're able to control the speed or whether you're allowed to vary the pump speed or fan speed or not. That's important. Second thing is, as I say, that are you looking to the inrush because of maximum demand issue that you need to consider that. Third, are we looking into energy saving? Yeah, like sharing by Derek too. Yeah, please consider that. I think that's important. Yeah.
Oh, that's good.
Thanks.
Thank you, Mr. Wong.
Yeah.
Okay,
Yeah.
Mr. Derek, how about you?
All right. So, well, thanks again. And I would like to say one of the key takeaway from my point of view is that so I mean one of the most challenging thing when building these variable primary systems. A lot of engineers when they actually come to build these systems and they get to do it like maybe once in a year or once in every 3 years. So in the frequency of involvement is slightly, not to say not very frequently, but if you get a chance to do it, take a deeper look into the application design, not just by looking at how we size the terminal units and the chiller sizes, but also look at the entire energy simulation from the beginning. Because once an investor, when they buy this kind of system, they would expect a certain baseline even during part load. It's not full load. They will look at the baseline and the part load, and this is where a lot of engineers, they are struggling to achieve. So the thing is that always, even when you finish building the system and go to the live system during commissioning, and even after commissioning, look at these data and actually optimize it as close as possible. But of course, you can always seek us or your seniors in engineering who are still dealing with all these challenges in the industry, because there's always learning all around. Yeah. So yeah, put a lot of focus in controls, dynamics, I would say. You can learn a lot from there. Yeah, thank you.
All right, thank you. Thank you, Mr. Derek. Okay, we have actually a question from the forum. That is one of our first questionnaire is from Mr. Salman Muradi. Okay, he is an active member of organization in industrial. That what you think in the main barrier of adopting to inverter VSD, especially in Asian. Hello? Can I repeat the question, Mr. Wong?
Is the question to me? Okay.
Yes,
Yeah,
Mr. Wong. Yes, I just mentioned Mr. Wong. Yeah, as
Okay.
an active member organization in the industry, what do you think the main barrier of adopting to inverters VSD, especially in Asian?
Basically, that I feel is very important is the knowledge. Okay, knowledge
Okay.
for everyone that when you apply, you see, of course, inverter you compare with other starting method, the blocking point or obstacles is because of price. You see, so when you look into the ROI, you see, this is something that will be encouraging, even though you are engineers or maybe you presented to your superior or maybe the owner of the building. This will be the attractive point. Yeah, thank you.
Yeah. There's another one more question from Mohammad Sirun. Currently, are we still using the reduced voltage starters such as star delta and auto transformers? As inverters have nearly 30 years in Malaysia already, yeah?
Yeah. It's basically that more than 30 years inverter in the Malaysia industry. But like I say, because of a cost, you see, like I explained, and also that some application is not required to vary the speed. You only need constant speed. So the traditional or conventional starting method still require because of the price and also the applications.
Okay, thank you, Mr. Wong. Okay, we have a question from Mr. Derek. Okay, this is from Sek Kai Ng. Okay, basically the concern of harmonic distortion is in terms of current. Any solution for variable speeds drive, and how much is the THD percentage for Danfoss VSD?
All right, so this is a very good question, and there's a lot for the single question that this would lead back to where we actually have to show in the simulation, the software, where I would actually encourage, the extra session just to answer this question, because it needs the software to be operating in our partner's office actually, but we can present it online, no problem.
Okay.
Thank you, and I'll drop you my email address, or they come to you. Thanks.
Okay, I believe this is for Mr. Wong. Thank you, Mr. Derek. Okay, from Mohammed Siron again. Is the variable speed chiller suitable for the Malaysian climate? We have almost a constant dew point temperature. By reducing the chiller speed, its discharge pressure will reduce and hence its condensing temperature will also reduce.
Okay.
Yeah.
Basically, that I say variable speed chillers is definitely one of the solution. If, as I say, that your load is at, there is an accession load on the chiller side, then you can consider by using inverter to reduce it, but not necessary. Like example, you have maybe 2+1 chillers, all the 3 chillers you are require VSD, but you can consider maybe one of them is VSD and the other 2 is constant type 2. Yeah. Thank you.
Okay, thank you, Mr. Wong. I hope there is more questionnaires from the board. There's any more questions? If no more, I would like to convey these questions to Mr. Wong. Which is your most memorable and successful project you have experienced in reducing energy consumption for your customers' pump system?
Yeah, as I said that the first project actually did Miami is talking about 15 years ago, when we try to encourage or get the industry to accept the energy saving. A lot of people basically that is not believe that the VSD able to help to reduce energy saving. So this product actually is the one of the factory that in Bangi. Yeah, I basically I don't want to disclose the name. As I said that the project successful reduced 25% of the energy consumption. You see, and also this device is proven into the market until today. I believe that inverter is one of the device that can help you to save energy. Please believe that.
Okay,
thank you. Yeah.
Thank you, Mr. Wong. Okay, the second question is how to choose the pump starter between inverter and soft starter.
Okay, as I say that very important thing, these 2 device actually is the electronic driven device. One is the thyristor technology, followed by IGBT technology for inverters. For you to consider soft starters, actually for us is first, is it constant speed? Okay, if this application is constant speed, then please consider soft starters. And also the size of the motor you should consider. If you say the size is big, then maybe soft starter is actually help you. As I said that in my presentation, soft starter is talking about maybe 3.5 times to 4 times or 4.5, depend on application. But also the soft starter manufacturers claim 2.5 times when it comes to maybe pumps or centrifugal applications. So this basically can help you to look into that. But bear in mind, soft starter is cannot control speed. And also it won't help you on the energy saving compared with the inverters. Yeah. Thank you.
Okay, thank you, Mr. Wong. Okay, back to Mr. Derek. Okay, there's a question for you. Okay, during the presentation, you mentioned about the bypass control is important. How do you characterize the importance of the bypass control in the chiller plant?
All right, this is okay, very good question, and I would say this is one of the common problems that is faced in our industry quite frequently. Okay, the reason that I say is important, it plays a big role on the compatibility between the production loop and the distribution loop. So what does it mean, compatibility? So this bypass handles both, okay, the mixing, also when it is not stable, that means if it's not stable, then it will actually attribute fluctuations of differential pressure in the system. So it causes instability between the production loop and the distribution loop. So, and what happens is that sometimes when the bypass is unstable during part load, especially during the early handovers, and this is where it trips the chillers and the pumps. So there's a lot of wear and tear if a bypass control valve is not selected properly. And it is the closest to the pumping source, which behaves using like a fire, which usually behaves like using a fire hose to fill up a glass of water or a glass of sake, we call it. So open a little bit, overspill. All right, so that's where we are also recommend a very good selection of the valve, especially you can actually use pressure independent technology on this part to solve the main problem. Yep. Thank you very much.
Thank you, Derek. Okay, that was a good analogy, yeah? Right. Okay, this is the question for you, Derek. Salman Muradi, he's asking, what is the simulation software Derek uses in the presentation slide?
Sorry?
What kind of software for the
simulation software.
Yeah.
Do you mean actually? I need the question to be slightly specific. Did you mean the hydronics software? Or
Okay, we'll wait for Mr.
Because
Salman Muradi to answer.
Mr. Salman.
Yeah.
Okay, Mr.
Okay.
Salman.
It's a
If
big
not, I will
wig,
just present. Yeah. It needs to be slightly specific.
Sure. No problem. Okay, I would like to ask a question too. Which is the most memorable, successful project you have experienced, Mr. Derek, in energy saving consumption for your customers' pump?
Okay, that sounds romantic. Actually, okay, the very romantic because I will tell you, I'm very surprised at some sites that the pump kilo. Okay, when we talk about pumping ratio, we are talking about kilowatt per ton, right? Especially we are looking at the main ratios. So when we look at pump kilowatt per ton, sometimes when you go to site, it's 0.3, and if you look at that ratio against the chiller can be 0.55, right? So it's almost half the chiller consumption of the compressors. And I would say the project that I'm actually the happiest to save the energy consumption is actually Wisma Consplant 1. And that's actually quite widely published. It's not a secret, and we have been dealing with PHB and the consultants also, YHS. They're actually very happy, and this is not a secret. So I mean, we have done the commissioning together, and that is also not just the pumping system, it's also a variable primary system. So which is consists of several main I would say major manufacturers put together. And that's where we also calculate, we use a software, hydronic simulation software, to calculate the critical unit where they actually pull the wires, the wires all the way from the plant room to the highest pressure drop point. But remember, it's not necessarily the furthest, it is somewhere in the middle of the system and link it back to the pump. So that is one of the first proudest project that I would say. And we have those documents to be presented. Yeah, thank you very much.
Thank you, Mr. Derek. Okay, back to Mr. Wong. Okay, this is a question. What will be the next generation of pump control system?
Okay, as I said that in my presentation, for the past, you're talking about on-off, then followed by pump controllers, the technologies. Then today, beside a pump controller, you have inverters that able to be work independently to replace maybe the pump controllers. The next, basically, that the generation or technology, I believe that the IoT is coming in. Okay, so and the cloud-based, all this basically you can help you. First, that you can remote do the adjust setting. And also maybe that you can also find the location. Allow you to allocate. Oh, where is my site today? Okay, maybe that you are the big company, MNC company, and also that you see all this will help you to basically look into the predictive maintenance. Okay, historicals, data trending, and also example you have alarm. All this is very easily. All this information can back to your PC. Or today maybe your smartphone. You see. So this will be a next trend that you're looking into. And also, if you say that is a company that they have a multi-site, you also can look into your energy consumption, right? That is a target for you individually. Oh, this year I need to basically reduce 5%, okay, say overall energy. From there, all this cloud-based will help you to look into that with the big data. Thank you.
Okay, thank you. There's a last question for Mr. Derek here. During your presentation, you had mentioned about the bypass control importance. How do you characterize the importance of the bypass control in chiller plants?
Yeah, I think there was a question that I answered previously,
Sorry. Okay.
and
So I think there's a repetition here. You have also
yeah, maybe
mentioned
it's
that the
on.
critical units. Are you okay? You have also mentioned that the critical units is not necessarily the furthest in the hydronics. I think you also explained that earlier. I mean, okay. How about the
It's like
invariable status that are sweet spots? How do you define the sweet spots, and how do you take advantage of it holistically?
okay. That's a also very good question. I would say I would like to bring up some of my slides to move on those dynamics and how we look at the system that holistically. So I would like to bring up my slides and we move a bit further on that. So now, yes, these equipments are more expensive, I would say. So, and of course, when you say more expensive, also we need to justify the return of investment, right? So when we look at the variable speed chillers, is that these characters are always the sweet spots are always defined during part load, and usually it's like a U curve. And and if we look at the green color character, and that is actually where we have magnetic levitation compressors that actually operates more efficiently than other compressors. So with this newest technology, right? So now, usually when we work closely with end users or designers, we would actually they would actually send us a table, and the table would actually we would actually plot out this area where we would simulate. Let's say the owner says that end user, okay, if I buy this kind of chillers, I would like to operate 0.47. And the second question they will ask us, I want to take full advantage of this. So what do I have to do? Then they said, I want to operate most of the time 0.47, which this is the sweet spot. And that means it's only operating, sorry, it's only has to operate between 30 and 80% capacity. Above that, then it will compromise the efficiency, right? So now, then we'll do a comparison, because normally they do not just see one, they don't just give us one threshold. They will give us two thresholds to compare usually. And also we also minimum do two thresholds, sometimes three or four. Threshold means the efficiency targets that they want us to achieve with this kind of chillers first, all right? Because it's the heaviest consumption. So what happens if we put 5 of these chillers together? And the main point here is these chillers are about 2,000 metric ton variable speed chillers. All right, and this is actually for data center. And when we look at this, is that when you put all these chillers in parallel, and this is also where you define the control strategy to stage in the chiller on based on load, so system load. All right, so you can see that the line doesn't go above 0.47 right here. All right. So, but of course, in between you will have lower point than 0.47. The only thing is that once it reaches to this point, which is around 8,000, maybe 700, and this is where the end users would need to make a decision whether they would have, because usually it's a 5+1 combination, 5 duty, 1 standby chiller. This is the standby chiller. All right, whether they should run a standby chiller to maintain efficiency, or whether they should keep running only 5 chillers, which compromises the efficiency. Either, so this is where we set an alert in the BMS. All right. So of course, if this is also where we can see at what load condition you have more chillers or less chillers. The lesser, the better the efficiency you want, then the part of this side here, this part here will be slightly more, slightly compromised on the capacity, unless you want to use the standby unit to maintain the efficiency. But of course, this can be seen during the system when it's running its analytics. And that's one. It's not so holistic yet. This is just a chillers. And when you have hydronic calculations and we size the pumps in the early stage, and we stack them together, we don't come up with just one bar chart and tell you, okay, this is the efficiency that you can achieve. But our team with hydronic calculations, we can size the pumps and the cooling towers together. All right, and then this is where we stack up. So we will be able to tell you at part load with all the heavy equipment stacked, what is the plant character like? And this is where we define the control strategy on how we should stage the chillers on to have a more efficient system maintained. So these are like the baseline set in the early stage. All right, so that concludes my I would say my answer for now. If you want more, then this is a hand-to-hand to work closely with you all to help your stakeholders to maximize the benefits. All right, thanks a lot.
Thank you, Mr. Derek, for the insightful tips. All right, now that we have come to the end, I would like to take the opportunity to say thank you to both the panelists, Mr. Wong and Mr. Derek, for sharing their thoughts and knowledge in this Power Talk. As the last note for our audience, congratulations as you are successfully staying in until the end of the MARVEX Power Talk. And we at the MARVEX are excited to welcome all suppliers, manufacturers to be on board and this business event to rebuild our industry together. So when you would like to discover how, would you like to discover how to be part of this business event? Or is it or in this Power Talk series? Our team has posted a link in the comment box, and click on the link to schedule an appointment with our marketing team for further discussion. So I would like to end this. Finally, do stay tuned for our new Power Talk session, and also stay safe and take care. Goodbye.
All right, goodbye, everyone. Thanks a lot.
Stay safe.
Thank you, Mr. Stay
Bye.
safe.
Bye, Derek.
Bye.
Okay, bye, Mr. Wong.
Bye, Mr. Wong. Bye,
Bye,
Mr.
bye.
Lee.